Okay, I did add, in case you're like wanting to see class announcements using the Twitter tool, you actually don't have to go through Twitter. You just have to go to your address and type in twitter.com EA_Snipes_CHM175, and then it will look like this. I think some of you might have seen that. Not like that. Almost. I wanted to point out the whole Twitter thing because you guys have a possibility that if you wanted to kind of see what things look like last year, you could, like last spring, a year ago for spring 2014, you actually could go here and see specifically what the tests were like. Because you know that I go over the tests. So if you want to take a gander of history, you go back to the Twitter feed. And since I've been doing this is the second year to do this. Okay. For instance, this is dated, well, September 25th. That's not a good example. That's an accidental post. But if you go down to here, you'll see May posts. And that actually was from, I don't know if this is making sense, May 7th of 2014. So it's wrapping back around in the Twitter feed. So if you go far enough, you're actually going to see some exams where I went over the exams. So that's a possibility. It wasn't all encompassed, or it wasn't complete for the semester. All right, so back to the syllabus, contact information. If you're going to be gone, kind of let me know. Though, if you're going to be gone, remember you have access to the announcements from the eCompanion site or Twitter. What else? All right, so bookstore. The thing about the bookstore is I love them, and they do good work, but they did not, you really do need a notes. They don't have the notes yet, do they? Okay, they just have notes. So what I do, what they will eventually have and you need to purchase is this. So there's part one.
Do you know when they'll have it?
I doubt if it's by Friday, but it should be by Monday. So, yeah, because it is a pain, because you would need to, if you want to keep it all together, put this into your spiral. Yeah, I kind of smiled when I finally figured that out yesterday. I'm like, oh my gosh. So my husband teaches this too. We're both scrambling a little bit. But I kind of smiled thinking, yeah, you guys didn't think we needed these notes, did you?
I thought it was weird.
Yeah. So, okay. But you can use the same lab notebook that you used to collect data last year. You can use the same goggles. Tomorrow we'll be checking into lab. It should be short, so should be all good. We're going to use Logger Pro again. I think you guys are probably good with that. Let's see if I can. Okay, so it's broken up into 4 units, and they're all awesome. It's kind of a standard inorganic chemistry, the second sequence of general chemistry 2. The unit 1, actually, the stuff I brought the toys for, we're going to be revisiting Lewis structures. So brush the dust off of that you know, and the Pauling values to kind of see the tug of war, electronegativity differences. Okay, and in unit 1, though, then we segue. That's very kind of eyeballish, kind of qualitative. Then in unit 1, we segue into some of the math stuff with Raoult's law, boiling point elevation, freezing point depression. It's kind of neat. We look at how matter transitions from a solid to a liquid and a liquid to a gas. It's pretty cool, which we've already looked at a little bit. We're going to look at more. We'll have a unit exam. In unit 2, we'll talk about how fast reaction rate, how fast reactions occur. Okay, you think they occur like that, or do they take a while? And there's a mathematical way to track that. So there's a fair bit of math. I would like to go ahead and do a study session again. I don't know if Wednesday afternoons work, or maybe tomorrow. You guys be thinking about it, and I'll try to kind of get it from you if there's a day that works better. So a little bit of math in Unit 2, okay? And then Unit 4, I'm looking for my pen. In Unit 4, we get to, basically it's a precursor to acids and bases. Unit 3. Unit 3 is a precursor to acids and bases, because finally in Unit 3 we are going to talk more about this sort of reaction that goes this way and goes this way. Okay, of course that's called an equilibrium. R for reactants, P for products, yeah. So it kind of goes back and forth. And only then can we talk about acids and bases. Okay, so we finish up with acids and bases finally. Unit 5, there's no Unit 5 exam. We will cover some stuff in electrochemistry. It's really kind of batteries and such. It's kind of fun. We talk about entropy, which is kind of fun in Unit 5. And so you'll see some of those questions on your final. Any questions about what that looks like? It's exciting. It is a little math intensive, but it's still pretty much algebra. Okay, you can kind of see the general broad course goals for Gen Chem 2. The assessment is the same. Okay, so you'll have almost every day we'll get to an assignment slide. We'll kind of go over the assignment a little bit again to kind of get you rolling, and that will be due the following lecture day. But I don't think we're going to get to an assignment slide today. We just lost too much time. So there'll be that homework. I'm going to throw out 10%. So honestly, it's not almost that you do it, but you need to understand it, the homework. No, it's important points, but not crazy important points. 4 unit exams and a final, and then your lab part. Your lab, semi-formal lab reports, the same as last time. Okay, I'll remind you how that looks. But 5% of your lab grade will come from doing those pre-lab things. So make sure you do those. Okay, lecture etiquette's kind of the typical. Well, I finally decided to join the 21st century. And I'm like, if you are expecting a phone call, like a text sort of thing, and you want to glance at and kind of respond to a text, I'm so cool with that. But carrying on a conversation, while somebody's trying to lecture, that doesn't work. That's distracting. Cheating, I think you guys will be fine. Exams we're going to give on Thursdays again. I think that works pretty good. And you can't use a graphing calculator for exams. And I don't give makeup exams, but what I will do is for your final exam, I will compare, if you missed a test, unit exam, your final will be substituted in for that missed exam. But if otherwise, I will compare your final exam with your lowest unit exam and make a substitution if it's in your favor. So the eCompanion site, I think, kind of looks like it looked before. Notice I tried to, if you want to, on the syllabus, you can change that 122 to 175. Well, I guess it would just be change the 22 to 75. That's what I get for copy and paste. All right. So grades will be posted again, and it does not hurt my feelings if you're like, hey, Mrs. Snipes, could you upgrade update the grades? And depending, I will say, oh, thanks for reminding me. So you can kind of see where your points are, kind of similar to Gen Chem 1. Okay, pluses and minuses. So this here actually, we'll be talking, when we check into lab, I'll remind you a little bit about the safety features. Tomorrow with check-in, we aren't going to play show and tell, so I think you guys are fine with your drawers. But, so you won't need goggles for tomorrow's lab, but you will need goggles for the next lab. I forgot to print out your lab schedule, and so I'll try to remember that on Friday. But we are doing Beer's Law in your experimental book, so experiment menu. And we're going to be doing Beer's Law, and we're going to be using those new CBL things. So, yeah, it'll be fun. Okay, think that's, any questions? All right. So then that other thing I gave you is some important dates that they tell us in their right, they, who double book rooms, right? That these are important dates to know, drop dates and such. When you get off, right? Okay. And I'll be reminding you of those when they come. And don't forget, with regard to weather stuff, remember I live in Burlington, so if the roads are bad between here and they don't have the foresight to cancel, make sure that you look at the instructor absent board. Okay. And don't risk your life to get to chemistry, right? Okay. Any questions? Cool. I didn't think so. Well, let's take a look at the handouts I gave you. And I mentioned Lewis structures, okay? I think in my lecture notes, nowhere do I say Lewis structures, but it's implied, okay? So we are going to talk about why matter sticks together. Have you ever thought about that? Why does one atom want to stick to another atom? We already kind of talked about that, but we're going to talk more about that. And that actually leads up to why does matter want to be a solid, or why does matter want to be a liquid, or why does matter want to be a gas? Okay, these things we call intermolecular bonds that stick matter together. And at the crux of it is something called polarity. Okay, is there polarity in the matter, or is there no polarity in the matter? And that almost sounds like it could be non-scientific, philosophical. Okay, but I'll kind of show you what I mean by that. Okay, so when you drew your Lewis structures, every dash that connected the atoms, that was a pair of electrons that stuck those two atoms together. That was a covalent bond. Okay, covalent bonds are a pair of electrons, and electrons are being shared between two atoms so that they'll stick together. Would that be an intramolecular, intra-bond? Okay, that's within the molecule. So just to kind of get the juices flowing here, everybody's favorite molecule. Okay, if we draw the Lewis structure for water, okay, we need to come up with a pot of valence electrons. Okay, with regard to hydrogen, there are two of them. Okay, hydrogen is atomic number 1, so that one electron is a valence electron. Okay, so 2 electrons collectively. With regard to oxygen, okay, there's 1 oxygen atom in water. Okay, but remember how do we know how many valence electrons an oxygen atom brings? Do you remember? 6. And how did you get 6? Yeah. Look at the group number. Exactly. Very good. You both got it. Cool. Okay, so we got to account for 8 electrons. You don't have to go through all these steps. You can just kind of jump to the final structure if you want. Remember, hydrogen only wants to, what we say, reach out once. So it's done. Okay, because there are 2 electrons here. Okay, so hydrogen is done because it's like helium. Does that make sense? I want this going just to kind of remind you of the structure. So we've accounted for 4 of our pot of 8. So we have 4 more, and so we are going to pair them up as lone pair electrons. So I'm going to choose green here. My X's are lone pair electrons. Okay, so those 3 atoms that make a water molecule, that's why they're definitely not linear, right? Let's see. Oh, yeah. I tried to organize. See, those blacks are different from these blacks. These blacks will give you that 4 things spreading, which is sp3 orbital hybridization. So I can do this. That would be oxygen, hydrogen, and lest we forget our forms. Okay, so that's a water molecule. Right? Covalent bond, covalent bond. Electrons are shared. Okay. So the deal is, and this is why I brought, we have it here on the slide, Dr. Pauling, right? Linus Pauling. He came up with these electronegativity values. They're chi. The Greek letter looks, it's Greek letter chi. Okay. So in the case of water, just to kind of remind you, the symbol for electronegativities is that, chi. And we're going to, I don't know if I have it up on a slide, but I kind of think it this way. I'm going to go ahead and write the water again. I'm going to go ahead and flatten it out just because it's easier. Okay. We could look at the difference in electronegativities between any oxygen and hydrogen. So that's kind of why I brought this. And you have it coming up. For oxygen, the value is 3.5. So chi is equal to 3.5. For hydrogen, the value is 2.1. And then let's just kind of finish that thought. There's something called delta chi, which is basically a little subtraction problem. Okay, so delta chi, we always take the absolute value of the difference between the atoms of interest to become up with the electronegativity difference between the two atoms that are joined together. Let no man put us under. Okay. So check me on this. It looks like 1.4. Does that work for you? Okay. So the delta chi is 1.4. Does anybody remember? It's in your notes. At what point does this electronegativity get so big that the one that has the biggest electronegativity absconds onto the electron? Electron is transferred. Do you remember kind of what that threshold is? I've probably 1.9 in some books. I've read it at 1.7. So 1.9, 1.7. Exactly. At some point, an electron would be totally transferred to the thing that has the higher electronegativity. Now, before we go on, oxygen electronegativity of 3.5, hydrogen 2.1. Let me go ahead and write one more thing on this cheesy model down here. The higher electronegativity means I'm going to go ahead and use a lowercase delta. It looks like an S with kind of a, okay, that's a lowercase delta, and it means partial. I know it's kind of strange, really, but it does. Anytime you see that in physical science, it means partial. So here, the oxygen is partially negative, and here the hydrogens are partially positive. Each one of them are, because we could do the same thing with the other hydrogen oxygen. Okay? Now, in our Lewis structure, and I know this isn't a complete Lewis structure because I don't have my complete octet because 2 lone pair of electrons are on the oxygen. But here, as it's drawn, this green dash means 2 electrons are being shared, but they're not shared equally. It's kind of cool. We have what's called an electropotentiometry map here in a minute. And basically, we're going to see that the electrons buzz around the oxygen more than they buzz around the hydrogens. Okay? So actually what I'm describing is polar or polarity. That is exactly what I've described. We basically have a polar bond, and the whole darn thing is polar. Okay, so I kind of got ahead of myself. Okay, so electronegativity. What Pauling came up with these values, they assume that an atom is going to be bonded with another atom. So this is the tug-of-war values, okay? So the higher the chi or electronegativity value, the more electrons are being sucked to that atom when it's bonded with another atom. That's why when we looked at oxygen having the higher electronegativity value than hydrogen, that's why it's more electronegative, it's partially negative. So there's all sorts of tug of wars going on within a molecule, because, you know, water's a molecule, right? It's pretty exciting. lots of words taken from that slide, huh? Sometimes I see you guys writing and I'm like, oh, I shouldn't have taken all those words. But that's okay. All right. So if we had a periodic table in here, I would point to the periodic table and I would say electronegativity. Now, this trend is just for the main group elements. So you have to remember when main group elements, we're talking about the A's. So we have 1A, 2A, we skip the transition elements, and then we have 3A through 8A. Okay, so basically take the S block and the P block, put them together. Electronegativity increases from left to right, and it increases from bottom up. Okay. I think usually. I don't know. You might find some exceptions. I don't know. So these are the electronegativity values, which I'm going to put on my refrigerator. So this chart is the same information as this. It's just showing you the higher the bar, the greater the electronegativity. Okay, and then that actually is what I've been holding up. So it's kind of small in your PowerPoint slides, but it might come in handy when you're trying to see what side of a bond, a chemical bond, which side of a chemical bond are the electrons going to be scooting to, like with the oxygen and the hydrogen. Okay. Well, so covalent bond is basically when two electrons are connecting a pair of atoms. It is possible that there's no polarity in that bond. It's possible that there's no polarity in that bond. That can only be the case if when you come up with the delta chi, and I'll go ahead and add this to this slide while you guys are writing, okay, you can have a nonpolar bond, okay, if and only if, set like this, if and only if the chi value of atom A is equal to the chi value of atom B. They got to be equal. And to me then, if you calculate the delta chi, what's the delta chi going to be? Electronegativity difference going to be if they're both the same. Right. See it all. And it could happen. It most likely happens. Do you guys remember some of my favorite elements, the Hoffer-nickel? What's Hoffer-nickel stand for? Very good. Yes. Yay. Each one of these elements actually floats around in its natural state, paired up. Okay. So those are really good examples of, having electronegativity the same. Not possible. But more than likely, when a pair of electrons are shared to make a covalent bond, there is a degree of polarity there, a certain amount of polarity, and that's always going to be the case, okay, if the electronegativities aren't identical. Now, so polarity is kind of like the tug-of-war thing, right? There could be a big tug-of-war where it's very unequal, or it could be just a little tug-of-war, and it makes a difference. So there are like degrees of polarities in bonds. So I'm going to underline the word bond up here. We are focusing just on the bond between atom A and atom B. We're going to have to, here in a little bit, I don't know if we'll get to it today, but we're going to kind of have to scale up from the chemical bonds, the polarity of a bond, to the polarity of a molecule. Basically, you look bond to bond to bond with a bird's eye view and to see what the molecule's doing. So I'm hoping, this should kind of seem familiar when we talked about covalent bonds and electronegativities. Okay, so speaking of familiar, here's your 1.9, 1.7 sort of threshold here. Okay, at some point, the thing that's got a high electronegativity will just be so, I want that electron will be transferred. And remember, metals love to transfer their electrons, and nonmetals will say, yeah, I'll take it. So nonmetals form negatively charged anions. Metals form positively charged cations. Okay, so the way this is arranged, though, if you look at the first the first 4 lines, okay, in all of those cases, electron will not jump the ship. In all those cases, covalent bond is formed between atoms A and B if their electronegativity difference is pushing 1.7. Okay, so just to emphasize over here, covalent means electrons are shared. Ionic, electrons transferred. I'll just say electrons. All right, that works. So just to kind of, a few slides to emphasize that. And again, I think this is a repeat slide. Here we have a pair of atoms that are joined together. And underneath on that scale there is the delta chi, so electronegativity difference. So what's the electronegativity difference in the first scenario, this Cl2? What do you think? If they both have the same Pauling value, take one minus the other and you get 0. Very good. And I'll just tell you, if you look up hydrogen and chlorine, it does have an electronegativity difference. The chlorine atom has the higher, what's that? 3.0. And what is hydrogen? 2.1. So what's the delta chi there? 3.0 and 2.1. Yeah, I agree. 0.9. I'm cool. That sounds good. So if you look at the slide before this, what did it say? The polarity of that bond is running, somewhere between weakly polar and polar.
Yeah.
Good. Okay, what about the electronegativity difference between sodium and chlorine? Chlorine 3.0, sodium 0.9. Yeah, I just have to get your calculators out. Yeah. So, does that all make sense? So just to kind of show on that middle HCl, though, I'm going to put a partially negative with the chlorine and a partially positive with the hydrogen. I love it when things are consistent. A few things in chemistry you're like, uh-oh, that's an exception, but a lot of times not. So we're still focusing on bonds that join 2 atoms, covalent bonds. Electrons not shared, but it may not be shared equally. So you could have a carbon and oxygen bond anywhere. I'm emphasizing this because, how do I say this? It could be anywhere, in any big molecule, little molecule, okay? But if you look at the carbon value is 2.5 and the oxygen value is 3.5, a difference of 1.0. So it's pushing pretty polar, right? Okay. And so the oxygen partially negative, the carbon partially positive, just a bond. Okay. Another convenient way to show the polarity of a bond, covalent bond, is this, and it works pretty well. It's kind of a vector sort of thing, where actually, to get down to the nitty-gritty, and we don't do much of this, but the length of this indicates the strength of the polarity, okay? So if this is 1.0 delta chi, if you had delta chi of 0.5, it would be half the distance. Does that make sense? Okay. And the front, you can almost see the plus where it's partially positive, and the tail of the arrow is where it's partially negative. So that works pretty good. So these are those electrostatic potential maps that show the hot spots of where the electrons are hanging out. So you can see where the electrons are really kind of hanging out a lot. It turns reddish. Where it's electron deficient, so something with a low electronegativity value would be kind of blue, okay? If it's kind of all over the map, it's yellow. And so you can see where the Cl2 molecule, electrons are just kind of spread out evenly. But if we compare that with HCl, where the chlorine atom has a greater electronegativity, it's turning red, okay? And if we compare that to actually where an electron is transferred, now that chlorine that picks up that electron from the sodium atom turns very red hot, and the sodium is blue. Okay. This is another way to look at without color, just kind of where the fuzz is where the electron cloud is hanging out. So again, if its electrons are shared evenly, like a H2, okay, molecule, then the cloud is evenly around it. Picking on something that is polar, hydrogen and fluorine. The fluorine's more electronegative, so fluorine actually has more of a cloud around it, okay, partially negative. And electron is entirely transferred between lithium and fluorine. Okay, so we've been talking a lot about bond polarity. Okay, atom A and atom B, that's bond polarity. Okay, we can use this. And I'm going to say that you use bond polarity to get this, to get molecular polarity. And it's almost like, well, the examples we picked were just two atoms, so there wasn't much expansion required, right? But I'll usually kind of say the bond polarity, and then I'll open up my hands and I'll say molecular polarity, which has an assortment of bonds, okay? So bond polarity, molecular polarity. Okay, because here's the deal. It's very possible, and we're going to definitely see some examples, where your molecule has polar bonds, but the molecule is non-polar. You're like, really? How can that happen? Well, I'm going to try to show you how that happens. So we're kind of switching gears, stepping out from our bonds towards our molecule, or looking at the molecule. So if somebody asks for your net worth, they're basically wanting to know how much you're worth. It sounds kind of cold, but they're wanting to know all of your assets. They're wanting to look at you and say, in some cases, that's what your potential assets are too. So, but it's collectively what you want. So a net dipole moment is basically looking at the individual, what? The whole picture, yeah, looking at the whole picture. Okay. Exactly. So this net dipole moment, I'm trying to see, this is an indication, or it summarizes the whole picture, the overall polarity. Okay, net dipole moment. And actually it has a value. And so, is it the symbol D? Or no, it's mu, darn it. Okay, so the symbol for net dipole moment is mu, like this, kind of like micro. The symbol for micro is the Greek letter mu. It's a U with a tail in the front. Okay, so that is net dipole moment. That's the symbol for that. And so basically, down here, I'm going to go down to the nonpolar. If mu, net dipole moment, for the whole molecule now, if mu is 0, okay, then the molecule is entire molecule. You'll just have to know that that word's supposed to be molecule. Molecule is nonpolar. Okay. Similarly, if mu, net dipole moment, is not equal to 0, then the molecule is polar. But here's where I told you to understand the polarity of a molecule, you have to start with the individual polarity of the bonds. And to understand, actually you have to also know the Lewis structure. Okay, so we'll get to that. In the meantime, I've just kind of, and I think this might be CO. You know, we looked at carbon monoxide a little bit ago, but actually we're just focusing on the bond. If we look at the molecule CO, you're going to see that the oxygen is partially negative and the carbon is partially positive. So what you're looking at, you can think of it as some cute little CO molecules, and they actually are between two plates that we can have electricity run between those plates, but the plates are off. Okay, notice it's polar. Okay, the partial negative, partial positive. If you apply an electrical current to the plates, such that one plate turns positive, okay, one plate turns negative, okay, notice what happens then is that the gas in between, assuming that carbon monoxide is a gas at that point, they rotate, okay, and so all of the carbon ends line up pointing to the negative plate, and all of the oxygen ends end up pointing to the positive plate. Isn't that neat? Okay, so there are some cool analytical tools that actually look for that rotation with the field applied. Okay, molecular polarity. Kind of comes from individual bond polarities, looking for a net dipole moment within that molecule. So, HF is pretty uncomplicated. Okay, two atoms joined together. You can kind of apply what we talked about before. The fluorine will be partially negative, the hydrogen partially positive. Now, the water molecule, I'm going to go ahead and tell you that the overall molecule has a net dipole moment. The net dipole moment is not 0. That makes the molecule polar. We still need to, and I think we're going to do it in the next few slides, still need to talk about how do you get a net dipole moment from the individual polarities. The next example actually is ammonia, not to be confused with the ammonium cation, which I hate, ammonium. Okay, so ammonia is neutral NH3. We drew the Lewis structure in Chem 1, and remember how that works out is NH3, you have the nitrogen atom in the middle, hydrogen, 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 and the way the pot of electrons work and such, you end up with a lone pair of electrons on the nitrogen. Aside from those lone pair of electrons, that has nothing to do with the partial negative. Partial negative comes from, if you look up nitrogen, 3.0, hydrogen, 2.1. See how this can be so helpful? Yeah. Okay. NH3 is also, like water, NH3 and water are both polar molecules. They have a net dipole moment that is not 0. Okay. So if a net dipole moment is this, to me then, the dipole moments are back kind of to the individual bonds. Okay. So I'm not going to hold you accountable, but it basically says if you want to focus on any pair of atoms, you can come up with a dipole moment mathematically. Basically, you take the charge of each of them, you multiply them together. That's what product is. Okay. And then you also multiply by their charges. You multiply them, the individual charges times each other, and then you include the distance that they're separated by. Okay, to get the individual dipole moment. So I'm not going to make you do that, obviously. But we can come up with individual dipole moments to come up with a net dipole. Okay, so we can do this. To me, it's a bird's eye view. Bird's eye look at the molecule to understand if this is water. Okay. It's a bird's eye view of the molecule to see if it's polar or not. Okay. Here's the deal. Sometimes I bring little tags. I don't have any little tags. But what kind of polarity do we have on the oxygen? Do you remember? Is it positive or negative? is negative. Very good. Partially negative. Cool. And then what about the hydrogens? Partially positive. Now this talks about finding, for every molecule like water, finding where is the middle of the positiveness and the middle of the negativeness. Right. Sounds like a dumb question, but where's the middle of the negativeness here? It's on the oxygen. Very good. All right, so spatially, cool. This one's a little bit different. Where is the middle of the positiveness? You got that? Seems like spatially. So here on the diagrams for water, you're going to see some figures. And basically it's going to say you do have polarity. And it basically goes from, here's the positive, up to that center of negativeness. So it goes from the center of positiveness up to the center of negativeness. You're going to see kind of that little arrow. That is the net dipole moment. Okay, so in this case, what I just described actually falls into the second category. Okay, for water, the positive and negative, that's the opposite charges. For water, those centers did not coincide. They did not. Because you told me this is negative, center of negative, and we'll make that. Center of positives here. There's a difference between their location. They don't overlap. So that's not always the case. Let me show you a case where they do overlap. Okay. This is a case where the negativeness and positiveness do overlap for CO2 molecule. If you were going to draw the Lewis structure of carbon dioxide, you would put the carbon atom here, double bond oxygen, carbon double bond oxygen. Now here's where it's important, we'll just use one last example. Here's where it's important that you can picture that that central carbon atom has undergone sp orbital hybridization. With that double bond, or I guess, yeah. Well, in any case, yeah, it's undergone sp orbital hybridization. So, since this is kind of the geometry of carbon dioxide, let's see, let's double check, make sure we got this right. Actually, it's on the builds, isn't it? Okay, the electronegativity of the oxygen atoms is greater. Okay, they have higher Pauling values. Okay, this is partially positive this time, partially negative. Okay, so where is the center of partial negativeness? On the orange atom, it's on the center. Where is the center of partial positiveness? That's what I mean by they coincide. They're at the same location. Okay, there's no little line to show a net dipole moment because they are in the same place. Okay, so that's why you see the mu value. That is the net dipole moment. Symbol for net dipole moment. Okay, it's 0. There's no little vector to draw between the partial positive and the partial negative. And then we'll just kind of finish up with this. Okay, so what you're looking at there is the water molecule. Okay. And we say that we can use these are vectors where the beginning is partial positive, the tail is partial negative. Okay. And then I like this diagram because it goes ahead and shows you the thing in yellow, the figure in the yellow box. It goes ahead and says just what I did up here. And the yellow box is taking between the two partially positive hydrogens and drawing up to the partially negative oxygen. Okay, and showing you where the polarity in that molecule is. It does have a net dipole moment. The molecule is polar. Very good. Well, I think that's a good place to stop. Thanks for going a few minutes later. And no assignment slide this time. Hope we don't have 2 assignment slides Friday. We'll see. But I'll see you on Thursday. And tomorrow I'll bring the lab schedule so you can kind of know what's what.